All right, welcome to another episode of the Base-12 Book Club, where I'm talking about my recently published book, Understanding Base-12 Math, How to Draw the Perfect Circle Using Dozenal Geometry. I'll put it up here for you so you can see. So what we're doing is just going through the book and reviewing the chapters one by one. We've already talked about the difference between Base 10 and Base 12. That's chapter 1, where I explained to you that there are some points on the Base 12 Cartesian plane that aren't accessible in Base 10. So on the other hand, there are points that are accessible. So an example of that would be point 5, which is half of in Base 10, half of the length of 1. We get this length, the length of 1. 0.5 in Base 10 is equal to 0.6 in Base 12. That's the midpoint there. Or if we were to travel to 0.9 in Base 12, that's to here, I think 9, we see that that's exactly halfway on this square. So that's 0.9 in Base 12 is basically 3/4. So we know 3/4, the decimal version of 3/4 in Base 10 is 0.75, 5, 6, 7, and then a half. So some points are accessible, but there you see you have to divide this smaller square into 10 and then travel along the length of 5. Well, here we just access it on the first iteration of dividing the line. But again, the length of 0.5 in Base 12 or 0.7, this point right here, there's no corresponding point on the Base 10, on the Base 10 line. No matter how many times we divide and make the lines finer and finer, we never get to that point. So we get a repeating decimal when we divide 7 by 12 or 5 by 12. So some people have said, well, you're just working in twelfths, and that's true, but on the Base 12 Cartesian plane, those specific points aren't accessible as they aren't accessible in Base 10 like they are in Base 12. So that's important to remember because that's always the first question everybody asks. What's the difference between Base 10 and Base 12? And it's just the fact that we're working on the Base 12 Cartesian plane, and the diagram that divides the circle into 360 degrees has to be constructed with those exact proportions, because this is important to realize that we're talking about precise and exact lengths. And if you're in Base 10 and trying to access it using fractions, you're always going to be a little bit off. So another question that I had was about the square root of 2 and just explaining, could I explain a little bit more how that works? So again, the square root of 2 originates when we have a triangle where the two sides of the right angle are the length of 1, and then the hypotenuse becomes the length of 2. And we can test that using the Pythagorean theorem, a squared plus b squared equals c squared. So I'm using this little triangle here because this is a little plastic triangle that you'll get in your geometry kit if you have ever purchased one. And you also get this little triangle here, which is the special right triangle. So what's unique about these triangles is it's their proportions. So no matter what length these two sides are, they're always going to be the same. And then if you want to find this length, you simply multiply this side by the square root of 2. So if this triangle had lengths of 3 and 3, this length would be 3 root 2. And if this was 0.1 and 0.1, this would be 0.1 root 2. So when you see the little squares on the diagram that are going at a 45-degree line, those are always going to be in units of square root of 2. And so the same is for this triangle. Here we have the dimensions or proportions where this side is the length of 1. This is always going to be twice that length, so 2. Then the bottom is square root of 3. So if this length was any number, like 73.5 or something, you could simply double that, multiply it by 2, you have the hypotenuse, and then you multiply that by the square root of 3, you'd have this bottom length also. So any triangle that has the length of 1 within its proportions, you can then easily calculate the other lengths of the triangle. So this is what I wanted to talk about in this video, is the importance of the fact that the Base 12 dodecagon is anchored on the Cartesian plane in such a way that the points are landing on the 1. The length of 1 is incorporated into the dodecagon structure. We travel along the x-axis the length of 1, and then we go up or down the length of 0.7, and that's where we find the points that define the shape of the dodecagon. So it's important to realize that this dodecagon pattern is completely sort of anchored or dispersed or permeates the Cartesian plane the same way that these triangles do. No matter where we travel along the x-axis, we're going to go up the same distance and there's always going to be a point that defines the line in units of square root of 2, or here it has a relationship to the square root of 3 and the length of 2 and the 45-degree angle and the 30-degree angle. So the dodecagon permeates the Cartesian plane. So I think it's on page 36 where I show you a picture of the rings of the dodecagon. So it's important to realize that those rings are also in between, and no matter what x-axis point you're on, there will always be a corresponding dodecagon that links up with those points. So that's what I wanted to mention in this video, really make it clear that the fact that it doesn't line up that way in base 10 makes it more of a, I'm going to say, mundane geometric pattern where it's interesting, you can sort of see it, but it doesn't connect to every single point on the Cartesian plane the way that the dodecagon does in base 12. Okay, so I just wanted to really stress that that's my big point for this video. In the next one, we're going to look at some geometric properties of the dodecagon that I didn't show in the book. So we're going to start to go into a little bit more depth, some of the geometry that I skipped over because I thought it was too simple. We did cover a lot of ground in the book, so I hope you're enjoying it. If you've read the book and if you're still thinking about buying it, there's a lot of good information there. We're just getting started now. We're looking at the different versions. You can see, well, I'll put it up here. You can see the importance or the relationship of the dodecagon to these two triangles when you sort of put them together, like, let's see, let's put that one there and this one here like that. You can see they have a relationship to each other. The dodecagon fits right in between those. You can see that on page 49. Where we have a line that's defined by the 45 degrees, and then it's inside, sandwiched between the 30 and the 60-degree line, something like that. So you can see that on page 49. I'll put that up here just for everybody to sort of see the relationship of the dodecagon to these two very important triangles. And we're going to just keep looking at that in more depth and see the implications. We're talking about the empty space that is sort of emerges between these triangles. And I'll also have a question for you in my next video to help me with something, because there's something I haven't quite figured out yet, and maybe some of you will be able to help me with that. All right, so I hope you can join me for those next videos. Thanks for watching.